Welcome, everyone. My name is Matt Del Bono, and I'm an Extension Support Specialist with the Greenhouse Lighting and Systems Engineering Consortium. Today, you're going to be hearing a State of the CEA Industry update from our Principal Investigator, Dr. Neil Mattson, and our Executive Director, Gretchen Schimelpfenig. The first video in this three-part series will cover New York State market growth. In the second video, we'll focus on technology development. And in the third video, we will cover technology adoption and impact. Before we get started, I want to take a moment and introduce you to our organization. At GLASE, our mission is to transform greenhouse lighting and systems management to support climate-smart CEA. To do so, we research LED systems engineering, plant photobiology and physiology, and greenhouse environmental controls to commercialize emerging technology, improve business performance for growers, and reduce the carbon footprint of greenhouse operations. GLASE partners include Cornell University, Rutgers University, Rensselaer Polytechnic Institute, and our founding partner is the New York State Energy Research and Development Authority, NYSERDA. At GLASE, we accomplish our goals through research and technology transfer. We also provide a broad range of educational opportunities like our courses, webinars, and other resources in our library. And finally, we seek to help the CEA industry network, build community, and generate business at our online and in-person meetings. Please reach out to our team if you are interested in learning more about GLASE and our member benefits, and thank you for tuning in.
Welcome back. We're now talking about how technology for greenhouses has been adopted, in particular, LED horticultural lighting. So, Neil, why don't you tell us again how GLASE projected LED horticultural lighting might evolve both in like first generation and second generation systems, and remind us of those units that we're going to be using to describe how performance has increased.
Perfect. Thanks. Let me start with units, and then we'll go from there. So there are kind of two different units that are used for efficacy of lighting fixtures, and essentially they both measure light output per unit of electricity. So a higher number is better. That means we have more output for the same unit of energy. So one of the units that was traditionally more used, like 5 to 10 years ago, was moles per kilowatt hour. So it's moles of light output per kilowatt hour. And we can convert that to the other unit, which is now used more frequently, which is micromoles per joule. Simply, we need to divide moles per kilowatt hour by 3.6 to calculate micromoles per joule. Okay, so now that we're on the same page with lighting units, let me think through the logic that we had with GLASE. So back in 2017, when we were putting the project together, status quo lights were primarily HID lights, such as high pressure sodium or metal halide fixtures. The best HID fixtures on the market had an output of 1.7 micromoles per joule. So that was the status quo that we were looking at. And by 2016, 2017, we were seeing some of the best first generation LED systems on the market were approaching about 2.6 micromoles per joule. So they gave us about a 35% energy savings. Then the hard part at that time was further predicting what the next generation of LED lighting systems would be. Diodes became more efficient over time. They were brighter. They delivered more light per unit of energy. And so our estimate at that time is that eventually we'd reach a point where efficacy had doubled. So we moved from 1.7 to 3.4 micromoles per joule, which would give us a 50% energy savings. We could get the same amount of light on our crop with half the energy used.
And so let's talk about how that panned out. So we polled our industry advisory board members and asked them about their feelings on how performance has increased over the years, and we did not achieve consensus. We discussed the baseline about how 1.7 is what we were sort of comparing to, but the reason there wasn't a huge consensus is because there are lots of different types of LEDs, some of them broad spectrum, some of them more focused spectrum with more red, which can influence the energy efficiency of the light. And so in general, some members agree that we can achieve greater than 50% energy savings from some LED products because there are some that have what's called a photosynthetic photon efficacy, PPE, which describes that second number we were talking about in micromoles per joule. Some of those products are out there that can have high PPE of 3.5, maybe even getting close to 4. And that does represent a 50% improvement over something like a double-ended high-pressure sodium. But there are others on the lower end of the bell curve that aren't achieving that 50%. And so we feel like our projection of 50% is achievable in today's world, but is it cost effective for every grower? Perhaps not. And also, there was a note from other members that noted that some growers, while they are using more energy efficient fixtures, are adding the number of lights, adding more fixtures to the same grow area. So while they're using maybe more efficient lights, they're actually adding more wattage to the same room or adding higher wattage LEDs. So the growers perhaps get more production or more yields. And so, Neil, do you want to comment on some of those findings about the types of LEDs, about how some growers are perhaps focused more on production than perhaps energy efficiency?
Yeah, right. So I like your point about the actual spectrum of light that you deliver affects the efficacy. So the most energy efficient LEDs that we have currently are red LEDs, and then blue is second. So the most energy efficient LEDs give us this purple looking spectrum, which is, say, majority red light and then a little bit of blue light. So some of those are definitely in the range now of 3.5 to 4. However, if we're interested in implementing more broad spectrum light, such as white LEDs, those are a little bit on that lower side of efficacy projections. And those tend to be implemented more in indoor operations where we don't have a background of sun that's giving us that broad spectrum of light. And then I very much resonate with the last observation, which is growers can kind of choose if we have a current electrical capacity of our operation, we could either use less of that with LEDs and be more energy efficient to deliver the same amount of light, or we could take advantage of that electrical infrastructure and energy efficient LEDs and deliver more light to get more yield out of that same area. So I would say, in a sense, we're not always saving electricity on a per acre basis because we're using those LEDs to get more light. However, we are driving higher yields out of that area. And so if we look at energy use in terms of, like, say, crop output, like kilograms of harvested tomatoes per kilowatt hour, I do think we can show those energy efficiency increases.
And that's why benchmarking is so important. And so we have one more update about activity in the industry from perhaps like the Design Lights Consortium. On the fixture side, we noted that technical requirements are continuing to kind of improve the efficacy of technology. And so version 3.0 increased PPE threshold by 21%. And so that means that LED-based horticultural lighting is a 35% PPE increase above the most efficacious non-LED option, like a double-ended HPS. This is lower than our projection of 50%, but there are some, like we mentioned, a portion of products that are available to meet our projections. And so in general, our updates today show that GLASE's projections of growth for the CEA industry, growth for lighting controls adoption, and growth for LED horticultural lighting adoption were close, and in some cases have been met and are being met by a portion of products and perhaps a portion of growers in our state as well as in the nation. And so we hope that you learned today about how over the past 5 to 10 years, the CEA industry has evolved and how GLASE is helping continue to research these new emerging technologies. Thanks for joining us today.